this video, I have already covered till classification of solids. Now moving towards crystal lattices and unit cells. The main characteristic of crystalline solids is a regular and repeating pattern of constituent particles. If the three-dimensional arrangement of a constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called crystal lattice. Thus, a regular three-dimensional arrangement of points in a space is called crystal lattice. A portion of crystal lattice is shown in figure 1.5. There are only 14 possible three-dimensional lattices. These are called Bravais lattices, after the French mathematician who first described them. The following are the characteristics of a crystal lattice. Each point in a crystal lattice is called lattice point or lattice site. Each point in crystal lattice represents one constituent particle, which may be an atom, a molecule, which is a group of atoms, or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. Unit cell is the smallest portion of a crystal lattice, which when repeated in different directions generates the entire lattice. A unit cell is characterized by 1. Its dimensions along the three edges A, B and C. These edges may or may not be mutually perpendicular. Second, angles between the edges, alpha between B and C, beta between A and C, and gamma between A and B. Thus, a unit cell is characterized by 6 parameters: A, B, C, the 3 sides, and alpha, beta, gamma, the 3 angles. These parameters of a unit cell are shown in figure 1.6. Primitive and centered unit cells. Unit cells can be broadly divided into 2 categories: primitive and centered unit cells. A. Primitive unit cells. When constituent particles are present only on the corner positions of a unit cell, it is called as primitive unit cell. And B. Centered unit cell. When a unit cell contains one or more constituent particles present at positions other than corners in addition to those at corners, it is called a centered unit cell. Centered unit cells are of 3 types. 1. Body-centered unit cell. Such a unit cell contains one constituent particle, atom, molecule, or ion at its body center besides the one that are at its corners. Second, face-centered unit cells. Such a unit cell contains one constituent particle present at the center of each face besides the ones that are at its corners. Third, end-centered unit cells. In such a unit cell, one constituent particle is present at the center of any 2 opposite faces besides the ones present at its corners. In all, there are 7 types of primitive unit cells: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. Their characteristics along with the centered unit cells they can form have been listed in table 1.3. Now one by one, I would describe all the crystal systems along with their characteristics. The first one is cubic crystal system. Its possible variations are primitive, body-centered, and face-centered. The axial distance or edge lengths are equal. A equals to B equals to C. Their axial angles are also equal, and all the angles are equal to 90 degrees. And the example of cubic crystal system is NaCl, sodium chloride, zinc blende, and copper. Now next is tetragonal crystal system. The possible variations are primitive and body-centered. Talking about their edge lengths, A is equal to B, which is not equal to C. The axial angles are all equal to 90 degrees, and the examples are white tin, SnO2, which is tin oxide, TiO2, and then CaSO4, calcium sulfate. Now next is orthorhombic crystal system. The possible variations are primitive, body-centered, face-centered, and end-centered. None of the edge length is equal. A is not equal to B, which is further not equal to C. Talking about the axial angles, all are equal to 90 degree, and the examples are rhombic sulfur, KNO3, potassium nitrate, and BaSO4, barium sulfate. Now the next is hexagonal crystal system. The possible variation is only primitive, and talking about edge lengths, A is equal to B, which is not equal to C. The axial angles, alpha equals to beta, which is equal to 90 degree, and gamma is equal to 120 degree. The examples are graphite, ZNO zinc oxide, and CDS. Now the next is rhombohedral or trigonal. The possible variation is primitive. Talking about edge lengths, A equals to B equals to C, and axial angles, alpha equals to beta equals to gamma, which is not equal to 90 degree. The examples are calcinite, CaCO3, and HGS, cinnabar. The next two are monoclinic and triclinic. Talking about monoclinic, the possible variations are primitive and end-centered. Talking about edge lengths, A is not equal to B, which is further not equal to C. The axial angles, alpha equals to gamma, which is equal to 90 degree, and beta is not equal to 90 degree. The examples are monoclinic sulfur, NaSO4, Na2SO4.10H2O. Now next is triclinic. The possible variation is primitive. Talking about edge lengths, A is not equal to B is not equal to C, and same goes with axial angle, none of them are equal. Alpha is not equal to beta, which is further not equal to gamma, and they all are not equal to 90 degree. The examples are K2Cr2O7, CuSO4.5H2O, and H3BO3, the orthoboric acid. Number of atoms in a unit cell. We know that any crystal lattice is made up of a very large number of unit cells, and every lattice point is occupied by one constituent particle, atom, molecule, or ion. Let us now work out what portion of each particle belongs to a particular unit cell. We shall consider three types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. First one, primitive cubic unit cell. Primitive cubic unit cell has atoms only at its corners. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure 1.8. 4 unit cells in the same layer and 4 unit cells of the upper or lower layer. Therefore, only 1/8 of an atom or molecule or ion actually belongs to a particular unit cell. In figure 1.9, a primitive cubic unit cell has been depicted in 3 different ways. Each small sphere in figure 1.9 represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures. The arrangement of particles is easier to follow in open structures. Figure 1.9b depicts space-filling representation of the unit cell with actual particle size, and figure 1.9c shows the actual portions of different atoms present in a cubic unit cell. In all, since each cubic unit cell has 8 atoms on its corner, the total number of atoms in one unit cell is 8 into 1/8, which is equal to 1 atom. Now the next is body-centered cubic unit cell. A body-centered cubic BCC unit has an atom at each of its corners and also one atom at its body center. Figure 1.10 depicts A. Open structure, B. Space-filling model, and C. The unit cell with portions of atoms actually belonging to it. It can be seen that the atom at the body center wholly belongs to the unit cell in which it is present. Thus, in a body-centered cubic BCC unit cell, 8 corners into 1/8 with per corner atom, which is equal to 8 into 1/8 and further equal to 1 atom. Now the next, one body-centered atom which is at its center, so 1 into 1, which is again equal to 1 atom, and total number of atoms per unit cell equals to 2 atoms. Now third one, face-centered cubic unit cell. A face-centered cubic FCC unit cell contains atoms at all the corners and at the center of all the faces of a cube. It can be seen in figure 1.11 that each atom located at the face center is shared between two adjacent unit cells and only half of each atom belongs to a unit cell. Figure 1.12 depicts A. Open structure, B. Space filling model, and C. The unit cell with the portions of atoms actually belonging to it. Thus, in a face-centered cubic FCC unit cell, 1. 8 corner atoms into 1 by 8 atom per unit cell, which is 8 into 1 by 8 1 atom. And second, 6 face-centered atoms into half atom per unit cell, which is 6 into 1 by 2 further equal to 3 atoms. So total number of atoms per unit cell is 4 atoms.